All right, so today we're looking at voltaic or galvanic cells. They mean the exact same thing, both the words. What makes voltaic or galvanic cells different than the other cell we're looking at is the fact that these cells are spontaneous. So if they're spontaneous, what do we know? What's positive? The voltage, the E naught or the E, is going to be positive, which makes sense because what voltaic or galvanic cells are batteries. So if we have a battery with a negative voltage, it's a dead battery. The way it pretty much works is this unit we are dealing with electrochemical cells. And they fall into two categories, the positive E and the negative E. What we're looking at today, the galvanic or voltaic cells, are our spontaneous ones. The negative E we're going to look at on Thursday. And those are our electrolytic cells that do electrolysis. And so we'll look at those separately. So today all we're really going to look at is the voltaic cell. So everything I'm showing you, all the parts you need to be able to do, I need you to be able to recreate whatever I'm showing you. And anything that I label or talk about, I want you guys to know. So when we start out, our old school voltaic cells were normally two separate vats. Two separate containers, okay? And in each, we normally have a liquid and a solid. Sometimes you can have two liquids with a semi-permeable membrane holding the other, but for the most part, we're dealing with a solid and a liquid in each of the cells. Each of these half cells has a half reaction going on in it. The half reactions come from whatever cell we're building. So until you get really good at this, I want you to write the half reactions that's going on in each of the half cells. So what do you want to put in this one, the copper or the cobalt? Copper. Copper plus 2 electrons makes copper. Does everyone see why I did that? Okay, we're starting with copper plus 2, it's becoming copper. So is this reduction or oxidation? Reduction. So what we have in the cell is an ion and a solid. The solid is always the electrode itself. And then the ion, we're going to have in a standard cell a 1 molar solution of that ion. Now, is it copper 2 from the shelf on the bottle? No, it's probably copper 2 nitrate or copper 2 chloride or something like that. But all we care about in our net ionic half reaction is that copper 2 ion. All right? So what would be the half reaction for the other cell? Good. CO goes to CO plus 2E minus. So we have solid cobalt hanging in a 1 molar solution of cobalt plus 2. Okay. For some discussion we're going to talk about later, cobalt plus 2 is a pink solution and copper 2 is a blue solution. And we'll talk about that in a little bit, but I'll ask questions about it. So this then is not reduction, it is the oxidation half reaction. So when this reaction goes, it's going to, yeah? How do you decide what is the solution? It's in the reaction. Ions can't be solids, and that's a solid because it's a zero oxidation state. That has to be a solid, that has to be an ion in solution. So if I were to ask you to find the voltage of this cell, how would you do it? Use the table. Correct. You would take the reduction half reaction, look it up, take that voltage, look up the oxidation half reaction. What would be wrong with it, though? You'd have to flip it because the table is just reduction. Take the opposite sign of that voltage and then add those two up to get the total voltage of the cell. And that would be E naught, the standard voltage. But what I care about right now is labeling the parts and where that voltage comes from. It's from the movement of electrons from one half cell to the other. So we're going to connect both of these with a wire. Now looking at the half reactions, we need to figure out direction of the electron flow. However, I want to name these electrodes. They have special names. One's going to be an anode and one's going to be a cathode. And you need to know which goes with what. Does anybody remember? I don't care about the charge. The charge is meaningless. The charge is just a label. That doesn't tell me which one the anode is by saying the anode's negative. What? I heard somebody else say something. Oxidation occurs at the anode. Reduction occurs at the cathode. There's lots of ways to remember it. I'll give you a couple of them. Some people use red cat and ox. Reduction occurs at the cathode. Oxidation occurs at the anode. I tend to kind of just, in my head, quickly lean toward the fact that vowels go together and consonants go together. I don't really care how you remember it. All right. Now, there is an arbitrary label on batteries. How do you know how to put your batteries into your remote control or wherever you're putting them? There's a positive and negative sign. That's just a universal indicator. I don't want you to try to rationalize that because there's so many things that go on in the cell, like ion flow from the salt bridge, and if you have electrolytic cells, it's opposite. That you're going to screw up if you try to rationalize it. You just need to basically memorize that cathode in the voltaic cell is positive, and in the anode, the voltaic cell is negative. And that's universally accepted when you're jumping your car battery. The car battery, the cathode's positive, except that it's what you all know the colors. The red is positive, and there's all these different things that you can use for that. But anywho, just know these labels. Don't use them to rationalize anything about the cell. So let's talk about the direction the electrons are going to go. I don't want you to look at the signs right now. What I want you to look at is your equation. This is why I'm having you write the equation. And remembering oil rig helps. Electrons will flow. Oxidation is losing electrons. Reduction is gaining. So they're going to go from oxidation to reduction or from anode to cathode. I remember it that electrons flow alphabetically. They flow anode to cathode. So when you're indicating that on your table, and I graded one of these about 4 years ago, and a lot of students would just draw arrows like this, and they didn't get their point for the arrow because the professors are like, oh, they think it goes through the liquid and through the glass. The electrons are going through the glass. And I'm like, no, they don't. So ultimately, you need to make sure you label that those arrows indicating electron direction on the wire, because the electrons are going through the wire. So what's happening then is your cobalt solid is losing electrons and turning into cobalt plus 2. So what's happening to this anode physically? It's degrading. It's shrinking. How do you remember? Anodes always shrink because they're anorexic. I came up with that. That is patent. I have that in multiple videos. It's the best thing I've ever come up with in my life, just FYI. So anodes will always get smaller because it's always oxidation, which means it's always going up in charge from that 0 to an ion. What's happening to the solution's color? What? Just look at this half reaction. You're taking solid cobalt, and what are you making? Cobalt plus 2. Cobalt plus 2 in solution is pink. What's happening to the solution? It's getting more and more pink. Okay? What's going on here in the cathode are copper 2 ions. They're going to be gaining electrons and actually depositing copper. So what's happening to this solution? It's getting less blue. And what's happening to the cathode? It's growing. Some people say fat cat because it is getting heavier. So if you were to weigh electrodes before a cell and then weigh them after, your anode would weigh less and your cathode would weigh more at the end of it. This is how we deposit metals onto jewelry and things like that. We make sure we hang this jewelry or do whatever that we're plating in the cathode portion, and it's then going to get plated with whatever metal, because you can do this to different kinds of metal, not just copper. Okay? All right. Now I have a problem with this cell. I'm going to get one electron, and it's going to go from here to here, and then all of a sudden we have a charge buildup. We have a negative overall here and a positive overall here. Why would more electrons want to leave a positive environment to a negative environment? They're not. So this is only going to last for like a nanosecond, and then it's done because something's missing. It's not being used. I heard someone say salt bridge. That is what we are missing. We are missing the salt bridge, which completes the circuit and helps neutralize that charge buildup. So we're going to put in a salt bridge. Now, we want something in our salt bridge that is not going to create a precipitate with anything else. We want something in our salt bridge, a salt, that's always going to stay as soluble ions. Any ideas? Okay, I'd be okay with NaCl in this particular case, but what if I had silver plus 1 going to silver? Wouldn't we make silver chloride and then we'd start losing silver from the salt bridge? So that's not a good option. I need something that's always soluble. A nitrate. And what should nitrates be paired with? Group 1, exactly. We want to put a group 1 nitrate in there. I don't care which one. What group 1 nitrate do you want to put in here? Potassium nitrate. Okay. Now, how does the salt bridge work? Again, don't look at these signs, guys. That's going to totally mess you up. You need to look at what's going on in the cell. Electrons are moving from anode to cathode. So as electrons are going this direction, we're getting a negative charge buildup in this cathode. Which ion from the two, the K plus or the NO3 minus, is going to just naturally migrate to the cell that's turning negative? The K plus. And that's what happens. The K plus naturally migrates there, neutralizing it so another electron can come. And that's how we get that whole thing going. When the electron leaves, what are we leaving behind? What kind of environment? Positive. So which ion naturally migrates into that? The nitrate. And you need to know the direction of ion flow. All right? So far, so good? Questions? All right, the very last thing you need to be able to do with this stuff is to find something called shorthand notation. It's basically a one-sentence thing that describes everything that's going on in here. Or if I give you the shorthand notation, you should be able to recreate all of this. Shorthand notation is always alphabetical. Oxidation first, then reduction, or anode, then cathode, either one, AC, air condition, run to the OR. There's a bazillion things you could do to help yourself remember it. But what you do first is you go to the oxidation or the anode half reaction, and you write what you see. First thing I see in this equation is CO. So I'm going to write CO, and then I'm going to put one line. And then I look at the next thing I see. Hey, CO plus 2. That's it. That describes everything I need to know about that half cell. And then I do my double line. Do you see how from this half cell I could now write that equation? All right. Do you see how this tells me 0 to plus 2, that's oxidation? I can get everything I need from this. So now I go to the other cell. What do I see first? Cu plus 2. Then I draw one line. And then what do I see next? Cu. So this is shorthand notation. So if you see it, you'll know that you need to, you know exactly what's going on. The only thing you might see differently in some problems, if you're not at 1 molar solutions, they might put a parentheses and write the molarity in parentheses next to the ions. But if it's 1 molar, you don't put anything, and it's assumed as such. Okay, y'all ready to try another one? Okay, this time we're going to put the anode on the other side. We've got a little bit of a different situation here. Take a look at what you're given, and don't answer out loud yet, but just think about what's different here. We've got an issue. I want to see if you can figure it out. Perfect. They don't tell us what's oxidized and what's reduced. They're just saying, hey, here's a bunch of crap, make a battery. Well, what are some things we have to take into consideration? What do we want this battery to have? We want it to be spontaneous. We want it to have a positive E. So we're going to have to figure out which of the reduction potentials should stay reduction and which should become oxidation. So my suggestion to you in a case like this is just take the components and really quickly write both as reduction half reactions. So how do I write copper and copper plus 2 as a reduction equation? Good. And if I were to look that on the table, it's 0.34 volts. Iron plus 3, I'm going to write them both as reduction. I need to start somewhere as a comparison basis. And if I look this up on the table, I see that's a negative 0.04 volts. Those are the reduction potentials. Which one of these, and we talked about this yesterday, is more apt to be reduced? The copper. The one with the higher reduction potential is the one that is going to be reduced. So what are we going to do to the other one? We're going to flip the entire equation and change the sign. We're going to leave copper by itself, though. So we're going to get iron going to iron plus 3 electrons and make that a positive 0.04 volts. So my overall voltage is going to be 0.38. Is that positive? Yeah, so that makes this spontaneous. Notice had I flipped that other one and made it the oxidation, I would have gotten a negative voltage. We didn't want that. We want this to be a spontaneous reaction. We want this battery to work. All right, so now that we know this, we can continue on with the problem. Which is our anode? Which is oxidation? The iron reaction. So I'm going to write that just like that. And then here I have my copper reaction. Okay, so my solid is my iron, and my 1 molar is my plus 3. Also, what is my cathode solid? Good, and then I have 1 molar copper plus 2 in there. Attach them with a wire. What's the arbitrary label on the cathode? Plus. Cats are positive, just remember that. Or there's a plus in the cathode. It's going to be opposite next unit, not next unit, next cell. Do you see up there where Vanna White is? It says EPA van. This is how you remember. Electrolytic, we haven't done those yet, but the electrolytic cell, positive anode, voltaic, negative anode. And that's what we're doing today. Okay? If you just remember van, okay, it's going to be opposite. So anywho, now we've got this going. What directions are my electrons going to go? Anode to cathode. So we're going to flow that way. But now I've got a charge buildup going on. I'm pretty depressed about that. So what do I need to do to fix that? Put in a salt bridge. What would y'all like to put in the salt bridge? Oh, let's be a little more creative. Thanks. That's so much better. NaNO3. All right. Electrons are flowing to the cathode, creating a negative charge buildup. What ion is going to naturally migrate to the cathode? Na+. I need to hear pluses. Y'all are dropping those things off like they don't matter. Sodium does not migrate to the cathode. If it did, it would explode. Sodium ions. What migrates to the anode because we leave behind a positive? The nitrate ion. Okay. The iron solution is a dark, dark, dark orange. It's that orange. We did the equilibrium when we made the FeSCN-. Remember that? It was the longhorn color orange, and you were finding that K was a constant. And then the copper 2 is blue. So tell me what's happening to colors as the cell progresses. correct. So our iron's getting darker, and the copper 2 is getting less blue. If I were to weigh the electrons after the experiment, which electrode, if I were to weigh the electrons, yeah, they don't weigh very much. If I were to weigh the electrodes after the experiment, which one would weigh more? Cathode, and which one would be anorexic? The anode, that would weigh less, okay? And then the last thing I want to do is shorthand notation. So, which electrode do I start with? Alphabetical, oxidation or the anode. What do I see first? Fe. I draw vertical line. What do I see next? Fe plus 3. Then I draw 2 lines. What do I see next? And then I draw Cu, line, and then Cu. And that's the shorthand notation for this. Okay? So I'm pretty much going to stop there. What we're going to do tomorrow then is I'm going to draw another one of these really fast, assuming you already know it, just to refresh. And then we're going to calculate this at non-standard conditions using the Nernst equation. This thing can be changed by changing our concentrations from 1 molar, and we're going to do that tomorrow. Okay?